Hello everyone, this is Mahmoud Ali, a PhD student at Indiana University. Navigation, mapping, and exploration are interconnected tasks. However, most of the existing approaches, such as the SAR project from ARL and other designs, implement them as a separate modules, resulting in efficient performance and sometimes better behaviors. So we propose a framework to unify the formulation of navigation, mapping, and exploration using Gaussian processes. And our main contributions are a local GB perception model, which detects the free space around the robot. Second, a global GB exploration map, which encodes the exploration status of the environment. And third, a new approach to construct the metric topological map of the environment. And our pipeline is explained as follows. First, we receive the raw point cloud from LiDAR, then transform it into a spherical coordinate and project it into a circular surface around the robot, known as the occupancy surface, where each point on the surface is defined by its azimuth and elevation angle and assigned an occupancy value based on its return distance. Then we use a sparse Gaussian process to model the probability of occupancy over the surface, where the main advantage of the sparse Gaussian process is that it replaces the N training data with an M inducing point. And this reduces the GB time complexity from N cubic to Nm squared, where M is much less than N. And we leverage the uncertainty associated with the SGB predicted occupancy to construct the variance surface, where the uncertain area in the variance surface corresponds to the free spaces around the robot. And we define the centroids of the uncertain area as GB frontiers. So GB frontiers are used as local navigation points. And since they are located in the center of the free spaces, the robot movement is aligned with the Voronoi diagram of the environment. And this behavior maximizes the clearance to obstacles and reduces the risk of collision. And we also leverage the uncertainty of another global SGB model to encode the exploration of the environment, where certain areas mean explored and uncertain area means unexplored. Our exploration map represents a full scan of LiDAR using only a single point. Compared to other occupancy mapping techniques, this saves a lot of computation and reduces the time required to update the map. And finally, since GB frontiers abstract the local navigable space around the robot, we use them as the main building block to build the metric topological map in such a way that when the robot enters an explored area, the robot location is added as an explored node. One of the GB frontier is selected to be the next navigation subgoal, and other unselected unexplored GB frontiers are added as frontier nodes for later exploration based on the shortest path from the robot location. We validated our approach in simulation and real-world experiment. The results from the simulated indoor environment show that our approach explored the environment faster and with less travel distance than the state-of-art frontier exploration and graph-based exploration. Then we changed our approach in unstructured simulated forest environment, where the smoothness of property of the GB was able to handle the noisy point cloud and extract the correct frontier at trail intersection, where baseline failed to complete exploration in this environment. Then we tested our approach in an indoor corridor to test its ability to detect correct frontier, to connect a closed loop in the map, and to navigate to the nearest frontier node when the robot is in explored area. Finally, we validated our approach in a real unstructured forest, where the robot was able to navigate using only the local perception and to detect the correct frontiers at a trail intersection and to construct the metric topological map in real time. In conclusion, our approach requires less time to update the global exploration map and explore the environment faster than the baseline and has a running time which doesn't explode with the operation time. Thank you.